Now we are going to discuss about the tangents to polar curves. First of all, I should say that this is a direct application on parametric differentiation. So if you are not familiar with that, please go back and refer to those videos, and then we can you can easily understand what we are doing here. Otherwise it will be, you will not get a clear picture about what we are going to do here, right? Okay, so, and there's another thing, right? Now when it comes to finding a tangent, that is directly related with derivatives, right? But remember, we did all those derivative stuffs in the Cartesian coordinate system, right? But now as we are going to deal with polar curves, remember I said in one of the videos for this section, we can coincide this straight line with this x-axis, with the positive direction of the x-axis, so that we can talk about both Cartesian points and the polar coordinates in the same diagram, right? So we have to do that association, we have to obtain that association in order to discuss the tangents, or shortly to differentiate these polar representations, right? So now from here onwards, for this part we are dealing with the polar coordinate system which is placed on the positive x-axis of this Cartesian plane, right? So differentiation will make sense when we are doing it in this way, right? And now let's start with an example, right? Let's say if we have the equation for the cardioid, right? Cardioid, and that is r is equal to 1 plus sine theta, right? And suppose we are asked to find the slope of the tangent line when theta is equal to pi by 3, right? Now and also remember, the cardioid is some sort of a structure like this, an inverted heart shape, right? So what we have to do here is, to find the slope of the tangent, we have to find the value of dy by dx. Now here we are in this Cartesian axis as well, right? So dy by dx will make sense, right? Because this is the x-axis and this is the y-axis. Dy by dx represents the the slope of the tangent. So it makes sense to differentiate these polar equations, right? And also we said that in this Cartesian plane, which we have the polar axis kept on the positive x-axis, we have these two relationships, right? X equals r cos theta and y equals r sin theta, right? And then we are asked to find the derivative of y with respect to x, right? So now since this is now by looking at this equation, we can say that x depends on theta and y depends on theta, so it's like a parametric representation, right? So this is kind of a third variable and we need to get the derivatives, right? So we just do what we did for the parametric representations, right? Dy by d theta times d theta by dx, right? And we can rewrite this as dy by d theta divided by dx by d theta. So it's just a matter of computing the derivatives from x equals r sin theta and y equals here x should be cos theta, x cos theta, and y equals r sin theta, right? And here there is another thing that you should kind of focus, right? Now when you are getting the derivative like this, right, that is the derivative of this thing, right? If you take this r out from the derivative and if you just differentiate this one like this, it is completely wrong. Okay, can you think of a reason why this is not correct? Just pause this video for a moment and think about a proper reason. Right, I will explain it with another example. Now suppose if we have two functions like this, how do I say that? Yeah, so let's name our functions, and now I'm going to explain why this thing is not correct. Okay, right, now just for that explanation, let's suppose we have two functions of this nature, right? X squared plus x cubed, and let's have another function gx, let's name it as sin x, right? Then if we need to get the derivative of the two functions, of the product of these two functions, we will be using the product rule, right? F dash gx plus g dash fx, right? Now all these functions depends on x, right? But well, let's say if instead of denoting this function as fx, what if we just write the function, what if we denote the function with this letter only? It's just f, right? But still this letter represents this function, so the product can be written like this, right? Gx, right? So just because you have this one here, this kind of a letter, is it allowed, is it possible to take this one out from the derivative sign? No, it is not possible, because the only place that they allow to take a certain thing out from the derivative and using it as a coefficient is when this thing is a number, when this thing is a constant, right? But here, although we did not indicate that this is a function of x, still it's just the same thing, right? So hence you have to use these product rules, because simply we cannot take these functions out from the derivative sign. So here also we have the very same thing. This radius r is not a constant, right? It also depends on r. So if we need to express the ideas correctly, we should write it as a function of theta, right? So at each and every point, this r value will depend on theta. So it is not correct at all to take that number out from the derivative, right? So this is the place you have to be careful when you are computing the derivatives, right? And once you identified these properties, then it's just a matter of applying the this product rule now to compute dx by d theta. The reason for computing dx by d theta and dy by d theta is because we need that to compute the derivative of y with respect to x, right? So here the equation of the cardioid is given like this. See, r depends on theta, so it is better if we can write it like this. Okay, so since r depends on theta, we have 1 plus sine theta, that's the relationship they gave, and we have cos theta. For this one we have that 1 plus sine theta times cos theta. Now here we are going to differentiate that product with respect to x, right? So you have to use the proper product rules to differentiate these two functions, right? So that means the derivative of let's say this one, and you can obtain the derivatives like this. It's just a simple application of the product rule. So once you know the dy by d theta and the x by d theta with this equation that I explained before, that comes from these parametric representations and the chain rule, we can easily compute the derivative of y with respect to x, right? And that will be this one divided by this thing, right? So we have this equation. Now in the question it asks to find the slope of the tangent at theta equals pi by 3. So we just have to substitute theta equals pi by 3 in all these places, right? Then we will, if you do the simplification correctly, you can obtain -1 as the answer.